The Middle East is running out of water. Iran is warning that parts of Tehran may need to be evacuated due to water shortages. Iraq's once mighty rivers now flow at half their historic volume. Across Syria, Turkey, and Jordan, farmland is turning to dust. Underground water reserves, aquifers that took thousands of years to fill, are running dry. It's a crisis, and it's getting worse. But in the middle of this water catastrophe, one country has the complete opposite problem. They have too much water. That country, Israel. On paper, this makes absolutely no sense. 60% of Israel is desert or semi-arid land. In the far south, rainfall can drop to just 25 millimeters per year, basically nothing. And yet, as of December 2025, Israel produces roughly 20% more water than it actually needs. How is that even possible? The answer lies in two engineering projects built 60 years apart. The first, in the 1960s, carved a 130-kilometer artificial river across the country, lifting water 257 meters uphill from below sea level to the southern desert. The second, starting in the 2000s, turned the Mediterranean Sea into a tap, building a desalination network that now supplies about 80% of the country's drinking water. This is the story of how 2 generations of engineering turned one of the driest countries in the region into the only one that never runs out of water. Let's dive in. The problem: a desert with no water. To understand how extraordinary this transformation is, we need to go back to the 1950s. At that time, Israel's population was exploding. Farms were expanding. The nation needed massive amounts of fresh water just to survive. But there was a problem. Israel had only one major natural water source: the Sea of Galilee, also called Lake Kinneret. Everything else, desert. The Negev Desert sat in the south, a scorching wasteland where temperatures regularly topped 40 degrees C, and weeks could pass without a single drop of rain. Groundwater was limited. Rivers were practically non-existent. So how does a nation survive when most of your land has no water at all? The answer was bold: create an artificial water network. The idea was to build a 130-kilometer pipeline system moving water from the Sea of Galilee, which sits 213 meters below sea level, all the way south to the parched Negev Desert. It would take 5 years, cost hundreds of millions of dollars, and employ over 4,000 workers. They called it the National Water Carrier, a project that would either save the country or bankrupt it trying. Building an artificial river. Now imagine building a system to carry water from a lake below sea level all the way to the southern desert. Sounds simple, right? It's not. The first massive engineering challenge is gravity itself. Water from the Sea of Galilee sits about 213 meters below sea level, but the national water distribution network it needs to feed into is around 44 meters above sea level. That's a vertical climb of roughly 257 meters. You can't just let water flow uphill. You need to pump it. And that's where the Sapper pumping station comes in. Instead of building a normal surface plant, engineers carved Sapper into the side of the mountain above the lake. Here's how it works. Water is drawn in through an underwater pipeline several hundred meters long, passing into a 14-meter deep shore reservoir. Then it drops down a vertical shaft into a hidden pump hall carved deep inside the mountain. Inside that hall, an 80-meter by 20-meter cavern, 21 meters high, sits a bank of giant pump units. Each one combines a vertical intake pump and a horizontal high-pressure pump with motors rated at more than 30,000 horsepower, roughly 20 megawatts per unit. Together, they push Lake Kinneret's water from minus 213 meters to plus 44 meters in a single stage. Think about that for a second. That's like lifting water as high as an 85-story building. From there, the flow shoots into 3 steel pressure pipes that merge into a 2.2-kilometer pressure main. That pipe carries up to 72,000 cubic meters per hour, about 1.7 million cubic meters per day, into the open Jordan Canal, where gravity finally takes over and carries water south. The original 3 underground pump units have been running since 1964. That's over 60 years of continuous operation. In the 1990s, a 4th above-ground pump was added, ensuring the heart of the national water carrier never has to stop beating. But lifting the water was only half the battle. From there, it had to travel through 86 kilometers of steel pipe, buried underground, drilled through rock and shifting sand, crossing farmland where every inch had to be restored afterward. Survey teams measured everything to the centimeter because one small mistake could stop the flow, or worse, burst the pipeline. And yet, it worked. By the early 1990s, the national water carrier was supplying about half of Israel's drinking water. At first, around 80% of its flow went to agriculture and only 20% to cities. But over time, that balance flipped as the Negev and other dry regions began developing. The system became the national lifeline for over 40 years, until Israel faced a new crisis. The lake starts drying up. By the early 2000s, Israel's population had tripled. The national water carrier alone couldn't supply enough water anymore. On top of that, a series of brutal droughts pushed the Sea of Galilee to its black line, the official level where pumping is supposed to stop to avoid permanent damage to the lake. If they kept pumping, they'd destroy their only natural water source. In 2002, the government made a radical decision: build a chain of massive desalination plants along the Mediterranean coast and make the sea itself Israel's main water source. The plan called for roughly 300 million cubic meters of desalinated water per year by 2010, and around 500 million by the mid-2010s. Construction moved fast. Ashkelon came online in 2005 with capacity for about 120 million cubic meters per year. Hadera followed in 2009 at roughly 145 million. Then, in 2013, Sorek 1 opened as the largest seawater reverse osmosis plant in the world at the time, designed for around 150 to 234 million cubic meters per year. By the mid-2010s, these plants together were already supplying more than a third of Israel's municipal water demand, and they didn't stop there. Sorek 2, the mega plant. In 2025, Sorek 2, also known as Beit Miriam, pushed desalination even further, adding another 200 million cubic meters per year in a single facility. That one project alone boosted Israel's total desalination capacity by roughly 35%. The winning bid to build and operate Sorek 2 came in at about 40 US cents per cubic meter, making it one of the cheapest large-scale desalination contracts anywhere in the world. But building a plant is one thing. Making it efficient enough to run at national scale is another. At Sorek 2, the engineering starts offshore. Instead of open intake pipes that suck in fish and debris, the plant draws seawater through subsurface intake wells drilled 20 to 30 meters below the seabed. Sand and rock act as a natural filter, stripping out large particles before water even reaches the pipes. Inside, water passes through banks of hollow fiber membranes, each fiber thinner than a human hair with pores measured in microns. They remove algae, bacteria, and fine sediment, protecting the main reverse osmosis system from fouling. Then comes the hard part: reverse osmosis. High-pressure pumps ramp the water up around 60 to 70 bar, similar to the pressure 600 meters below the ocean's surface, and force it through thin film composite membranes with pores around 0.0001 microns wide. That's about 1/100th the size of a virus. Salt ions, heavy metals, and most dissolved chemicals are left behind. The water that comes out is almost too pure. It's slightly corrosive. So the plant adds carefully measured amounts of calcium and magnesium, adjusts the pH to a neutral range, disinfects with UV light, and adds a trace of chlorine so it stays safe as it travels hundreds of kilometers through the national network. In total, Sorek 2 can produce roughly 550,000 cubic meters per day. At typical household use of 100 to 200 liters per person per day, that's enough drinking water for between 2.7 and 5.5 million people. Because of the shift to the sea, Israel could finally ease the pressure on natural lakes and aquifers. In the early 2000s, the country was still pumping around 500 to 513 million cubic meters per year from the Sea of Galilee. By 2018 to 2019, that had fallen to around 25 million cubic meters, a 95% reduction. The infinite loop, using water twice. But Israel didn't stop at making new water. They also learned to use the same water twice. The Shafton wastewater treatment plant near Tel Aviv now processes around 400 million liters of sewage every day, sending treated effluent through underground pipelines to irrigate farms in the Negev. Nationwide, about 94% of wastewater is collected and treated, and roughly 87% of that is reused, mostly for agriculture. That's by far the highest reuse rate in the OECD. The next country on the list, Spain, reuses only about 20%. So here's the system as of December 2025. Desalination supplies most of the drinking water. Recycled wastewater covers a huge share of irrigation. Almost every drop in the system does at least 2 jobs before it's allowed to leave. By 2020, the problem had flipped. Desalination plants along the Mediterranean were producing more water than Israel needed in a typical year. Even as the Sea of Galilee remained vulnerable to the next big drought, engineers floated a radical idea. What if desalinated water could be pumped backwards through the national water carrier and into the Sea of Galilee itself? No country had ever tried anything like this at a national scale, piping desalinated seawater into a natural freshwater lake as a strategic reserve. Israel would be the first. Reversing the river. The National Carrier Flow Reversal Project took about 4 years to build and cost roughly 1 billion shekels, around $250 to $300 million US. New pipelines were laid to connect coastal desalination plants like Hadera and Sorek into the existing carrier. Dozens of kilometers of large diameter pipe, up to 1.6 to 2 meters wide, were manufactured off-site, hauled on multi-axle trucks, and welded together section by section. Existing pumping stations designed for downhill flow from the lake to the south had to be rebuilt to push water uphill instead. New high-pressure pumps and backup generators were installed so the system could keep running even if a unit failed or the grid went down. All of it is tied into a central control center that monitors pressure, flow, and water quality in real time. In late 2023, the system was switched on. For the first time, water that started in the Mediterranean Sea was pumped inland, up through the reverse carrier, and into the Sea of Galilee. Initial capacity is about 5,000 cubic meters per hour, with plans to roughly triple that to 15,000 cubic meters as more desalination plants and pumps are added. The results. Today, Israel runs a circular water system like no other. Seawater becomes drinking water. Cities and farms use it. Then 94% of wastewater is collected, treated, and 87% goes straight back to irrigation. Surplus desalinated water now flows backward into the Sea of Galilee, ready for droughts or sharing with Jordan. In just 60 years, a desert became a powerhouse. Regions that were barren in 1959 now produce 60% of Israel's fruit and vegetable exports. But the story isn't over. Recent studies suggest that by 2065, Israel may need up to 3.7 billion cubic meters of desalinated water every year, roughly 5 to 6 times its 2020 output. One analysis estimates that reaching those levels could require building around 30 new desalination units over the coming decades. Several more projects on the scale of Sorek 2, and then several more after that. Think back to 1959. Israel faced what seemed impossible, building a nation in a desert with almost no water. By 1964, they had constructed a river that didn't exist. By 2025, the country had built one of the world's most advanced desalination networks. Sometimes engineering doesn't just solve the problem, it changes the rules of the game. Final thoughts. So there you have it. A country that shouldn't have any water now has more than it needs. While neighbors face catastrophic shortages, Israel created an infinite loop, turning seawater into drinking water, reusing almost all wastewater, and even pumping surplus back into natural reserves. It's one of the most brilliant water systems ever built. What surprised you about this story? Drop your thoughts in the comments. I'm genuinely curious. And if you loved this engineering miracle, hit that like button and subscribe, because what's coming next is absolutely insane. Picture two countries locked in an engineering race to build the tallest structure humanity has ever created. A skyscraper so tall, it literally pierces the clouds. A tower that makes everything else look tiny. One was supposed to be finished years ago, but stalled halfway. The other already claimed the record, but might lose it. It's a battle of ego, engineering, and billions of dollars. And only one can win. You don't want to miss this one. Thanks for watching. See you there.